some examples, some properties which basically you don't see in the real world, and maybe some problems that people are working on. But we have also a time constraint, so don't expect too much from me. Although I said in the beginning that I might touch some complex analysis of several variables also. I'm not sure I can reach up to that, but we'll see. Depending on time availability, we'll do as many things as possible. Okay, so let me first share my screen. Okay, so I'll start with some brief history about complex numbers. Complex numbers. I'm not going to define them. Only I will trace a very brief history. So it's commonly believed that complex numbers arose from the need to solve quadratic equations. Equations like say x squared plus 1 equal to 0. But surprisingly, complex number actually arose from the need to solve cubic equations and not from quadratic equations. And the reason behind this is the following. See, when you see an equation like this, x squared plus 1 equal to 0, well, since there is no real number, x square is negative, so I would say that it has no solution at all. Okay, but the situation is very different for cubic equations. It's a fact that if you have a cubic equation with real coefficients, then there is always a real root. Okay, so you need some method to now find this real root. Okay, so first let's write this arose from the need to solve cubics. Okay, and Cardano was the first to write down some methods for solving cubic equations. So this is, I'm talking about 16th century. Okay, so Cardano brought methods to for solving cubics equations. It's a different story that Cardano actually he didn't himself discover this method, but actually he took it from someone. But that's a fun story to hear some other time. But what is interesting, in this method, even if you are interested to find the real solution, sometimes it requires to manipulate the square root of negative numbers. So there was a need to formalize this numbers, and it took some time. Only so late 18th century, these numbers were formalized. So late 18th century. Sorry, complex numbers where so this square root of negative numbers, basically they were properly defined. Complex numbers were properly defined and developed also. You had the usual rules and all, so everything was proper now. But then again, it took another century for the development of the subject complex analysis. That is where you study functions, complex differentiable functions, and also. So that was like the history. So another century. So this was maybe I write 19th century. 19th century complex analysis. that usually you take a course now in complex analysis that is from the 19th century. Okay, so complex analysis means we study complex differentiable functions. So this is what I'm going to start with. Okay, so complex. I'll simply write CPLX for complex derivative. So I'll quickly define this. So what it means. So suppose you have a function, the complex valued function, say defined. So domain of definition of the function I have to specify, right? Define near some point say P, near a point. I have to mention what do I mean by near. Near a point P. So C denotes the set of all complex numbers. And when I say near a point P, I basically mean that there is at least some disk where the function is defined. Okay? And for convenience, if you want, you can take the domain of definition of the function to be all of C. No harm, okay, for this talk. But you don't need to have the function to be defined everywhere. It's enough to know that the function is defined near some point P to talk about differentiability at point P. And how do we define this? Is called complex differentiable at P if the following limit exists: f of P plus minus f of P divided by H. Okay. Now, when you talk about limit, you need some kind of distance. So here the distance in the complex plane is the usual Euclidean distance between say 2 points in our Euclidean distance. Okay, so that is the distance involved here for limits and all. The distance that learned in coordinate symmetry in school. So now, if this limit exists, then we call this the function is complex differentiable, and the limit is denoted by then it is this limit is denoted by f prime at P and is called the complex derivative of f at P. Just one second. Okay. All right. Now you see, if you look at this this definition, this is exactly similar to the definition of differentiability in for real functions, right? Functions from R to R. The only difference here is that all the quantities are complex numbers. Okay. So one would expect that the usual properties, or the many properties of differentiable function, real differentiable function that actually follows from definition should hold here also. And that's true. For example, the usual properties like sum or product or quotient or maybe composition of complex differentiable functions are complex differentiable. And also the standard rules like product rule and quotient rule and the chain rule that you learn in calculus 1, they actually are true for complex differentiable functions, simply because of the definition exactly looks like the same. Okay, nothing else. Now, what is so at this point, one question actually comes to our mind, which is the following. So you see, when you have a function of complex numbers, a complex valued function of complex numbers, we all know that complex numbers can be thought of as vectors, right? Vectors in R2. So such a function, complex valued function gives rise to a function from R2 to R2. It's a function of two real variables and with two components. What is happening? Okay. So I want to talk about so basically complex versus real differentiability. Okay. So so you write z equal to x plus iy, and the function sz. So sz is also a complex number, right? So you write f as u plus iv. So these are basically real and imaginary parts of f. So then the function, this z going to fz, this gives us a function from R2 to not exactly all of R2 unless your function is defined on all of C. So we were dealing with a point P is equal to a plus iv, right? Near the point P plus a plus iv. So when you think complex numbers as vectors, so this function actually gives you a function like this: x comma y going to u of xy, v of xy, right? The function of two real variables. Now, students who have already taken multivariable calculus are aware of differentiability of such functions. So the first year student can skip this part of the discussion for the time being. But anyway, I'm going to briefly tell what exactly it means to say such functions are differentiable. So here, differentiability for such function you cannot define as limit of quotient like this, simply because division by a vector is not allowed, right? So one basically defines differentiability in terms of linear approximation or first order Taylor expansion. So basically the functions which are first order Taylor series expansion, first order Taylor series expansion, they are called differentiable. Okay. Now the question is, we have now two notions of differentiability. One, which is easy enough to understand even for first year students, this existence of this limit. Another is the multivariable calculus notion of for this kind of function. So the question is there any relation between them? Okay. So it turns out that the complex differentiability is a stronger notion. So that is, if a function is complex differentiable, it is differentiable in the real sense also. So so suppose f is complex differentiable at P. Okay. Then the following holds. So one, so you can say that f is real differentiable, okay, at P. That means, so now I'll write, okay, this is fine. So this means that there is a real linear map, right, from R2 to R2. This approximates f near the point P, all right? But then the question is, it also turns out that there are, functions which are real differentiable, but they are not complex differentiable. That is, this limit for such functions need not exist. So the question is, what is more expected from a real differentiable function so that it becomes complex differentiable? To answer this question, you see, one basically examines this limit. So in the complex plane, so when I say that h goes to 0, there are many ways to come to this point 0, right? Unlike in the real line where you have basically two options. You come from the left or you come from the right. Here you have, many options, many directions to come towards this point, right? You can come along curves, you can, come along straight lines, or there are a lot of infinitely possible ways to come to the point P. Now, if one exploits this fact, then it turns out that look at this function. These functions actually become, they partial derivative exist at the point AB, and they satisfy certain equations. This is basically ux at a comma b is equal to vy at a comma b, and uy at a comma b minus vx at a comma b. So these equations are called, these are partial differential equations. So these are called the Cauchy-Riemann equations. Okay. So the name Cauchy-Riemann is because of the following reason. Actually, Cauchy already obtained this from his limit, from existence of this limit, and he mentioned that this equation contain the whole theory of passes from reals to complex. Okay, and on the other hand, Riemann, he basically put these equations at the beginning of his function theory, and everything he consistently built upon that. That's why we call it Cauchy-Riemann equation. But let me also tell you that neither Cauchy and nor Riemann actually were the first to discover these equations. They already appeared. So this was, Cauchy obtained this in. Cauchy obtained in. Let me see. So. So what was the date? So it was in 1840. Okay, so Cauchy obtained this equation in 1814. Riemann developed, his function theory based on this thing. But already in 1754, in the work of D'Alembert, these equations appeared. Not from complex analysis, of course. That time it was not there, but some fluid flow work. These equations already appeared there, and it also appeared in the work of Euler and Lagrange before Cauchy. So these equations were there, but their connection to complex analysis was not known. Okay. Okay, so this is all about complex differentiability. We will need to know for this talk. With this, I also want to talk a little bit about complex integral calculus, so that we can move forward. Okay. So, all right. So. Okay, so I have to tell you something. So what we have just seen is that if your function is complex differentiable, then it is the real differentiable, and real and imaginary part satisfies these two equations, right? It turns out that these are also sufficient to conclude that the function is complex differentiable. This is basically if and only if condition. Okay, if and only if both of these conditions are satisfied. Let me briefly mention why that is true. See, the moment you say that f is real differentiable at P, there is a real linear map approximating f, right, at P. And we know that for this map, so this is a map from R to R2. The matrix is a 2 by 2 matrix, which basically consists of these partial derivatives of U and P. Okay. Now, if you look at the second, condition, this exactly ensures that this linear map is actually a complex linear map. A priori, it was the real linear map, but this condition ensures that it is complex linear. It's a standard exercise in complex, so not complex, in linear algebra. Show when is the map from R2 to R2, which is a priori a real linear, is complex linear. Okay, this precisely is the case when the matrix looks like A, B, and minus BA. This is the condition for that. So this is an if and only if condition. Okay, we are going to see some more equivalent, formulation for complex differentiability. But let me first introduce you to complex Integration is basically in the complex plane is basically line integral. So that is integration along paths. Okay, so the whole lecture is completely mute, right? So let me verify that I'm still audible. Okay, I am audible, right? And
yeah. Sure, you're audible.
Okay, okay. Feel free to ask questions, okay? So that I also know that everybody is alive. Okay.
Sure.
Okay, so how do we define line integral? This is so basically you need a path in the complex plane. So say gamma. So by path I mean you have a function from an interval a comma b to c. Usually when you say path, it only means continuous, but for this course we'll assume, for this basically talk, we'll assume that this is continuously differentiable. Continuously differentiable. This is in the usual notion. You see, it's a function of one real variable only, and you divide the real and you separate the real and imaginary part. Basically, you get two functions of functions from R to R. Okay, so when you say this is differentiable, this is in the calculus one. It's both the real and imaginary parts are differentiable, continuously differentiable. That is, derivatives are also continuous. That's what I mean. Okay. And suppose you have a function f continuous. So this is a complex value function, and it is continuous on the image of gamma. So image of gamma is this set in the complex plane. So you have a function defined on this image set, and it's continuous. Okay. Then we define this integral over gamma. Just the notation. Okay, don't worry too much if you haven't seen line integral and all, but especially the first year students. So this is simply defined as it's in the usual way. So you just substitute z to be gamma t. Then this looks like, so you change this to a to b. Gamma is defined on a to b, right? And so I am substituting z of z is equal to gamma t, and dz is simply gamma prime t dt. Okay, the standard trick. We don't want to go into details and all, but for computation you always go by this. Okay, so in fact, to be comfortable with this definition, because I'm going to use it for some time, let's even take a very simple example here. Suppose I take gamma t to be the following part or curve, where say 0 is less equal to t is less equal to 2 pi. So this is basically the unit circle, right? And so as t moves from 0 to 2 pi, you go actually in the counterclockwise direction. The parameterization always gives you an orientation. Okay, so now if I want to say different integrate over gamma, the function 1 upon z. So 1 upon z is you see away from 0, this function is continuous. So in the image on the image set, right, image of gamma, this function is continuous. So we can talk about integration in this from this definition. So this is going to be 0 to 2 pi. Then I have to substitute z is equal to e power it. So this is e power it. And dz is, so you differentiate e power it with respect to t. So this is I times e power it dt, right? This is basically, so this 2 pi I. Correct? So this is how one calculates line integral. Very simple. Okay. Right. So now, so this now if in calculus, let me keep it for some time if you want to see more. So now in calculus, you see, you basically have two big notions. One is that of differentiability, another is integration, right? And we all know that they are connected by the so-called fundamental theorem of calculus. there are basically two versions. One deals with integral of derivatives, and another one deals with derivative of indefinite integrals. So in complex analysis also, we have fundamental theorem of calculus. So let me state this. Okay, fundamental theorem of calculus for complex analysis. So here also we can state basically two versions. Version one is say integral of derivative. That's very easy to in fact derive. It follows from the single variable calculus itself. So let me state it. So version one. So you have some part gamma, and you are dealing with integration of gamma, right? So f is so when I write this, always assume that f is continuous on the image state. But suppose I know that this f is of the form some other f prime. So what is f prime now? So f is capital big F is basically say it's a function defined on some neighborhood of this curve near this comma, and there it is complex differentiable. So it is complex differentiable in a neighborhood of gamma, and it satisfies this equation on say basically you have to we should assume that f is even continuous. F is defined and continuous more precisely on this neighborhood. So small f is defined on this yellow region and continuous, and I know that f is of the form f prime on this yellow region. Then it turns out that this guy is actually it doesn't depend on even the curve, but it only depends on the endpoints, the p and q. This turns out to be capital F at q minus f. So no matter whatever curve you take inside this region, this integral always turns out to be this capital F at q minus capital F at p. So it's kind of path independent. This part is very easy to derive from the single variable fundamental theorem of calculus. But what is difficult is the second version, where you want to talk about indefinite integrals. So the result is the following. See, for this one needs to talk about an indefinite interval is going to look like, say, maybe I'll write it as a variable z, and you want to talk about. I should put a question mark because what I'm going to write apparently will not make sense. So I want to integrate from some point, say p, to z, a function, say f of zeta d zeta. Okay. Now, see the integral, as I said, it is line integral, right? You need a path to integrate. So here is the z. You have to choose some path to talk about integral like this. But there can be many paths from p to z. Okay, so there is some ambiguity here. Which path you are going to choose to talk about integral like this, because it's first of all integral as defined. It is going to depend on the curve, right? Curve is used to integrate. So unless your domain is very simple, something like say the whole complex plane, there is no canonical way of choosing paths. if you're walking on the whole complex plane, then given a fixed point, you can say that, well, any point is joined by the straight line segment, from that point to that point, because there is a line. But in general, you might work with very complicated domains, So for example, suppose you are, working on some domain like this. This is your D. Then, given a point, so you think this as a fixed point. So given a point Z, there may not be a canonical choice of path. So for example, if I take a point, say here, then I cannot, come by a straight line. Here you can join by a straight line, but here you have to come like maybe something like this, So there is no canonical choice of path. So to talk about something like this, you first need to make sure that this is well defined. And here comes the great theorem of Cauchy, one of the central theorem in complex analysis that's going to help us here. So what does this theorem tell you? So let me first talk about Cautious theorem. So to talk about this, I need to define a few things for you. So first, I want to, so suppose you have, sit like this. So first I need to talk about, what is a domain. So I have already used the word probably domain. See, first you need to know what is an open set in the complex plane. Open sets are those sets, where for example, you take any point, you should be able to find some disk around that, which always lies in the domain. Okay, so again, the first year students can avoid this thing if you are not very comfortable. You can just take it, the whole plane as the complex plane. Of course, then there is a canonical way of doing this, but don't worry about that. So open sets are those sets where you take any point, you can find a disk around that point, maybe very small, okay, but it lies in the domain. The second, I need to know notion of connectedness. So connected set means given any 2 points, you should be able to join them by polygonal lines like this. So I'm talking about connectedness in the complex plane. There is a more general notion of connectedness for arbitrary space. So, we are not going to talk about that. But for the complex plane, it's basically a set is connected, and you can join any 2 points by polygonal line segments. So this is so domain means. When I say the word domain or region also is used, so this means open plus connected. Okay. I also need the notion of simply connected domain. Simply connected. Intuitively, it is easy to define, though the actual definition requires a lot of information. But students in multivariable calculus know the intuitive way of defining this. This basically means that the domain has no hole. For example, let's look at, say, so I'm going to draw a domain, and suppose this is the domain. Okay, there is a hole here. So once you have a hole, if you draw a, say, a loop around this hole, then you cannot shrink this loop to continuously or to a point by remaining inside the itself. But on the other hand, if you look at a domain like this, so you take any loop anywhere, you can continuously always shrink. Forget about the continuous word, so it might be in a continuous fashion. Basically, you can always shrink it to a point by remaining inside the domain itself. So basically, you imagine a picture of this where there are no holes. C is, for example, simply connected because there is no hole. On the other hand, if I look at the punctured plane, where this point is removed, then this is not simply connected, because if you take a loop like this, you cannot continuously shrink it to a point because there is an obstruction here. So domains without hole, they are called simply connected, and domains with holes are not simply connected. Well, that's what you have to understand here. So this domain here I have drawn, purposefully simply connected. So what does Cautious theorem say is the following. So if let D be a simply connected domain. And F from D to C holomorphic. I haven't defined the word holomorphic. So holomorphic means, it is differentiable, complex differentiable at every point in its domain of definition. There is a reason for this special word. In the real world, you don't see. If a function is say complex, if a function is differentiable on an open set, you simply say differentiable. You don't use separate word. In the complex plane, when a function is differentiable at every point of a domain, we use this word holomorphic. And there is a reason for this, which you are going to see very soon. Okay. So that means complex differentiable everywhere in D. Okay, and suppose let's take this D to be the domain, this yellow part. So the theorem, then Cauchy's theorem says the following. Well, actually, you don't need simply connect it here, but let's take another problem. So suppose you have a disk centered at some point B, which completely lies inside the domain, together with its boundary circle. So D, P are say, inside the domain. For this part of the theorem, you don't need to take simply connected. You can ignore this. You just take a domain. Okay. So what does this theorem says is that this notation, when I put a bar, it means that this together with its the boundary circle. Okay? Let's call this boundary circle. So this theorem says that Cauchy's theorem. So integration over C f zeta or fz dz is equal to 0. Okay? So I'll just cut this part because the way I said it, you don't need simply connected. Okay? So you take any domain, then the Cauchy's theorem says that integral of in fact, so I'll slightly change the statement because I see that I have to use this here, and then it's better to do it for simply connected things. So let D be a simply connected domain. I change back my words, simply connected. And I don't take a disk now here. I take any loop. Okay, it's a little more general version of Cauchy's theorem, but anyway, I'm not giving any proof, so there is no harm in stating the general version. Suppose you have a loop here. Okay, so the loop means it's a path with initial and same endpoints are same. Okay, so gamma, a loop in D. Loop means a path with same initial and terminal point. So then it turns out that integration over gamma of fz dz is 0. So this is Cauchy's theorem or our Cauchy-Gorsuch theorem. Okay? Cauchy. See, Cauchy initially stated and proved his theorem for functions which are complex differentiable and derivative also is continuous. But Gorsuch realized that this additional assumption of continuity of the derivative is not necessary. The moment you assume that the function is complex differentiable everywhere, the theorem is true. So that's why you call it Cauchy-Gorsuch theorem. This is a great theorem. No, most of the results in complex analysis, when you read, you will see that are based on this particular theorem. Okay. Now, coming back to the second version of this fundamental theorem of calculus. Now you see this essentially tells you that the integral of a function is path independent as long as you are in simply connected domain. Because you see, say suppose this is one path from P to Z, and this is another path, say beta. And you call gamma the path, which is basically you first go from P to Z along alpha, then you go from Z to P in the reverse direction of beta. So we write it as alpha minus beta. Well, then integral over gamma is nothing but integral over alpha, this part. And this part is negative of beta, right? So this turns out to be, you can verify it from the definition that this looks like integral of gamma is basically integral of alpha minus integral of beta. So the left hand side being 0 is same as these two being equal, right? So that is path independent. So once you are in a simply connected domain, simply connected, and f from f is a holomorphic function from D to C. Cauchy's theorem guarantees that this makes sense. You can choose any path from P to Z. This function is well defined. Thanks to Cauchy's theorem. So this theorem implies well defined. And once you know that, it's not very difficult to check that. Right. So once you know that, it's not very difficult to check that this resulting function, this capital F, is actually holomorphic on D, and F prime is equal to F. Okay. So this is the second version of fundamental theorem of calculus. If you recall, in calculus, you basically integrate a continuous function on an interval, right, to get an antiderivative. Here you are integrating a holomorphic function, okay, to get an antiderivative. So holomorphic functions always have antiderivative. This is analogous to the fundamental theorem of calculus that you learned in calculus 1. Great. So we have fundamental theorem of calculus also, thanks to Cauchy's theorem. I now want to talk about some consequences of this theorem that will point out many differences between the real and complex world. Okay. So this was in fact our aim to talk about in this lecture, right? Okay. I have to keep a track of my time. Okay, I have time. So some consequences. So the first thing I want to talk about, I need to mention something called Cauchy's integral formula. So what does this formula tell you is the following. So if you have, say, a domain D, okay, and some holomorphic function, and suppose I have some disk. Let me draw a bigger domain. You don't have to take simply connected now. Okay? It's just the domain. And suppose you have some disk inside it. So this is the point P, and you have a disk of radius R, and it's closer. So that is the this open disk together with the boundary circle. So this is suppose inside D. Okay. Then the Cos integral formula tells you the following. You take any point inside this disk, that then you can recover the value of the function at this point z by means of the following formula. So you integrate the function on the boundary circle. So you call this circle C with respect to the following kernel, 1 upon zeta minus z, together with this 1 upon 2 pi r. Okay? So you can recover the value of the function inside the disk by integrating it over, on the boundary with respect to this kernel. So this is called Cautious Integral Formula. And you should know, it turns out that now you see, look at this actually is a function of z, right? It turns out that one can actually differentiate this function under the integral sign. Of course, all these things need justification, but forgetting that, so let's see if we differentiate this guy. So what do we get? So forget about the justification that you will learn in complex analysis course. So if you differentiate this under the integral sign, so this looks like, so variable, I am differentiating with respect to z, right? So you get 1 upon zeta minus z is derivative is zeta minus z squared. The minus 2 minus will get cancelled. Okay, so this you have also a formula for, this is the integral formula for derivatives. Okay. So there is the reason I mentioned this is the following. See, when you have a there is a thing, if you have a lecture in mathematics, it is not complete without a proof. Okay, so I want to escape. I want to talk about at least some theorem with proof. Simple enough, of course, so that it is accessible to everyone. Of course, it is based on something which we haven't learned much. We just have the definitions and all. So this theorem that I want to talk about is it's also going to give you some applications of complex analysis. This theorem is well known to everyone from schools, although you don't see a proof. This is called the fundamental theorem of algebra. Okay, and most of us already know that it says that if you have a polynomial with non-constant polynomial with complex coefficients, then it has a root, right? It has a root in C. Okay, so I want to talk about this theorem and give you a very, very short proof using complex analysis. Okay, before that, let's examine this integral formula once again, and see some consequence, some particular case of this actually. Suppose your domain D is all of C, and your function f is bounded. Well, then you see, you can take, so you are in the complex plane now. The point P you can choose to be 0. Given any point Z, I can draw a large circle around like this, right? In fact, you can take R, once you have one R, you can take, any R larger than that, it will still accommodate the point Z. So you can take larger and larger circles to accommodate Z, right? Circle centered at 0. But then you see, if you draw a very big circle of radius, radius very big R, say, this guy, so F is already bounded. This guy, is something like, the integral is something like 1 upon R square, right? The circle will have length 2 pi R. So altogether, if you walk a little bit, you can actually see that this guy will behave like 1 upon R, the whole integral in this setup. That goes to 0 as R goes to infinity. Okay, of course, it requires a little bit of work, but easy enough. Okay, so this would mean that the derivative at every point is actually going to be 0. Like in calculus, you can show that such functions are actually constant. So this will imply that f is constant. So this is called Liouville's theorem. Okay, so you have a holomorphic function on all of these. Such functions are called entire. And if you know that this function is bounded, then it has to be constant. Okay, so I'm going to use this to give a very short proof of the fundamental theorem of algebra. Of course, it has many proofs. Okay, but this is one of the simplest proofs. I don't know if anything simpler exists. So it can also be proved directly using Cauchy's, Cauchy's theorem itself. But then you need to talk about, some linear algebra is required, like eigenvalues and all. So in that sense, this one is going to be a little more simpler. So what does this theorem say? This theorem says that if so any non-constant polynomial in Z, okay, with complex coefficients as a root in C. Okay. So actually, once you prove that it has one root by factoring and induction, you can actually show that it has as many roots as the degree counting multiplicity. So the difficult part is to show that it has one root. But thanks to Liouville's theorem, proof becomes very simple. So you take Pz to be, say, E0 plus A1Z plus so on. Say A and Z for n with a non-zero. Okay, so it's a non-constant polynomial and it's a positive integer. Okay, and the coefficient you take non-zero, degree and polynomial basically. So the proof is by contradiction. So we assume that P has no root. Then what happens? You look at the following function, 1 upon Pz. Now this is, you see, because the denominator does not vanish, this is actually holomorphic, complex differentiable everywhere, right? Holomorphic on C. And it's a calculus exercise to show that, absolute value of this actually goes to 0 as mod Z goes to infinity. So, if you are very far away from the origin, the function 1 upon P is actually very small. Near the origin, some continuity and compactness arguments, so don't worry too much about all these things. Tells you that the function is bounded 1 upon P. So altogether, this actually implies that 1 upon P is bounded. Well, now you apply Liouville. This implies that 1 upon P is constant. This in turn implies that P is constant, which is a contradiction, right? So our assumption that P has no root is false, hence P has to have a root. Okay. So this is a very short proof of fundamental theorem of calculus. Algebra. So the only step is here is this calculus step that you have to verify. Everything else I have provided. There is no gap here. Okay. So only thing is, this is a calculus exercise. You should be able to do this. Okay. Of course, you are using something called Liouville's theorem, but that's all right. Okay, so I have successfully given you the proof of at least one theorem. So I am that with this. Now I want to talk about, as I told, I want to talk about some differences between TL and complex analysis. Let me keep, yeah, okay, I have some time, and I also started late, right? So I'll do that. Another consequence of the Cauchy integral formula is the following. You see, Cos Integral Formula is something like this, right? F of zeta is 1 upon 2 pi I integration over some circle. Oh, Fz I will write here. So this is happening on some circle like, so zeta is a point, this zeta is varying on the boundary and there is some point inside. So Cauchy actually, obtained the following. So this guy, zeta minus z, you can, expand in a geometric series. So as follows. So you look at 1 upon zeta minus z. You bring the center into the picture. And use the following fact. You see, zeta is farther from P than Z, right? Because Z is inside, zeta is on the boundary. So you write this as right. Now, once you write like this, this is of the form 1 by 1 minus something, which has absolute value less than 1, right? Because Z is nearer to P. So this has a, you can expand it in geometric series. So this is going to look like 1 plus Z minus P by zeta minus P plus Z minus P by zeta minus P squared, and so on. All right. Now, if you substitute this guy here and you integrate, of course, you need some justification, why you can integrate. For example, you have an infinite series. I want to integrate it term by term. This is where Weierstrass come into the picture. The Cauchy, of course, realized this can be done, but that time uniform convergence notion was not there. Okay, later on it was developed by Weierstrass. That's why when you talk about complex analysis, three big name comes: Cauchy, Riemann, and Weierstrass. It's usually called Cauchy, Riemann, Weierstrass function theory. Weierstrass formalizes everything. So he had given proper proofs of various facts. Now, assuming all this notions that you can integrate term by term. So this function, now if you substitute this here, it looks like, so fz is of the form. So the first term is 1 upon zeta minus P. You are integrating out zeta, so this is going to be some constant. Then you are integrating 1 upon zeta minus P squared. So what is left is some constant times Z minus P plus. You will get a series like this. And remember, this is happening inside, for all Z, inside this disk. So in other words, inside the disk, I have a power series expansion of Z, right? And it's known that power series can be differentiated as many times as you want. So this means this in particular implies that the function, which is a priori assumed to be only complex differentiable once, now has to be infinitely many times complex differentiable because it has a power series, expansion. And if you exploit this fact, so once you know that this implies f is infinitely differentiable, you can use that fact to determine this coefficient from this series itself. For example, you see A0 is equal to, I substitute Z equal to P, then everything else here vanishes. This is simply FP. What about A1? To get A1, I differentiate once, this constant disappears. This is just A1 now. And everything else has some Z minus P, so this will vanish. So this will become F prime P, and so on. So this FZ actually basically looks like now F at P plus F prime at P into Z minus P. I'll write a factorial 1 here plus, because the next term is going to look like something like this. So this is Taylor series of F at P, right? All of you, have seen Taylor series in calculus. So this is a complex Taylor series basically. So what it's saying is that now if a function is holomorphic, then near every point it has its Taylor series is equal to the function itself. Okay, so this means that the function is complex analytic. So this F is complex analytic. Okay. This is something certainly you don't see in the real world. So this is a good point to talk about some differences. Let's look at some real variable examples. So let's look at the following function. Fx is equal to, say, x times mod x. So this is from R to R. Okay. This function, see, mod x is not differentiable at 0, but I'm looking at x times mod x. Okay, so this is basically x squared. If x is greater or equal to 0, and minus x squared if x is less than 0. This function you can check that differentiable everywhere. In fact, you only need to check differentiability at 0. Okay, you can check that that is true, and its derivative is actually given by the absolute value function. Okay, this is a simple exercise. So this is a function, you see, this is differentiable everywhere in R, but derivative is not differentiable. That phenomena doesn't happen in complex world, right? We have seen that a function, once it is complex differentiable on an open set, on a domain, sorry, it is actually complex differentiable so infinitely many times, not even once, it's infinitely many times. This shows that that is not the case. Another beautiful example is you look at say, this is another example from calculus. You look at e to the power minus 1 by x if x is say positive and 0 if x is equal to 0. Right? So you have seen this function in calculus. You were basically asked to show that all the derivatives of f exist at 0 and equal to 0. F 0 equal to f prime 0 is equal to f double prime 0, so on, is equal to 0. So this is an infinitely differentiable function from R to R, and all derivatives at 0 are 0. So in other words, if you write down the Taylor series of this function about the point 0, z is identically 0, right? Coefficients are 0, so Taylor series of f at 0 is 0. But you see, function in the neighborhood of 0 is not identically 0. On the positive side, it is strictly positive. Here the function is strictly positive. Here it is of course identically 0. So this means that this function is not equal to its Taylor series in a neighborhood of 0. Again, you will see that this doesn't happen in the complex world. Once a function is once complex differentiable, it is actually analytic. It's equal to its Taylor series near every point. That is another big difference. Okay, and this example, is important from another point of view. Which I'll mention, and I'll stop short. Don't worry. So it is from the complex analyticity or the power series expansion. One can actually check the following. So suppose f is holomorphic on the domain D. Okay? Then zeros of f are isolated. Okay, so what does it mean? Isolated means, so if you say this is a domain D. If you find 1, 0, you can find a tiny disk. It can be very, very small, doesn't matter. You can find a disk around this 0, such that there is no other 0 apart from P in this disk. So between any two zeros, basically you have certain gaps. Okay. On the other hand, if you go back to this here, this function, if you look at, so you see this function is say a finitely differentiable function, but it is 0 identically on one side, but this side it is non-zero. So it has non-isolated 0. You take any 0 on the negative side, no matter whatever neighborhood you choose, no matter how small it is, you will get another 0. This phenomena doesn't happen here. I should say that unless f is identically equal to. If you take the constant function 0, of course, this doesn't make sense. But if you have a non-constant function, then zeros are always isolated. Okay. Okay. So so what else? So hi. How much time more I can take actually? Depending on
I guess we can. I mean, around 10-15 minutes at max, I guess.
10 minutes is good enough. Thank you. Yeah.
Sure.
Okay. All right. So this guy. So this basically this theorem, isolated 0 thing, it gives you another fact. If you have say two functions f comma z on the holomorphic, and suppose I know that f equal to z on some disk. Okay. Or maybe you can take small open set. Okay. So whatever. But that's okay, because inside an open set you can find it. Suppose f and z are holomorphic on D, and they agree on some disk. Then look at the difference. This guy is also holomorphic, right? but then it has non-isolated zero on this particular disk, right? Every point is a zero. This theorem immediately implies that this has to be identically zero, correct? Zeros has to be otherwise isolated. So that means that f is equal to z in all of these. So if you have two holomorphic functions on a domain, they agree on some tiny open subset of the domain, they have to be equal everywhere. Okay, this is called identity theorem. Okay, and this has many applications. One is basically it allows you to extend the domain of definition of a function. To talk about so I want to show you a beautiful example. So see, we are familiar with this series, summation 1 upon n power s, right? This is the Dirichlet series, and this actually converges. You can take complex numbers, but this converges for real of s bigger than 1. Okay? And one can also check that it's holomorphic for real part of s bigger than 1. So this is the complex plane. So this is, I'm taking the variable now as s. So in this region, this series converges and defines a holomorphic function. And it is also the fact that there exists holomorphic function, that the holomorphic function on all of C except at 1, that is equal to, let's call for the timing, this is f of s on. So I can find a function holomorphic, everywhere except at this point, not this line. Okay, so this point, so this is the line. So this is one. This is the line f equal to. So so there is a function which is defined and holomorphic except at 1 and agrees to this series here. This is a large open set in fact, right? In C minus 1. So the identity theorem guarantees that this function is unique. So it is unique by identity theorem. This function is called the zeta function. Okay, you might have heard about a zeta function, right? So this zeta function is defined like this, and it was Euler who observed that this guy, this in fact is Euler found a connection between this series and prime number. So this looks like this product is over prime 1 upon 1 minus e power minus s. So this gives a connection between this series and number theory. And understanding this function, more precisely the distribution of this function is a very important problem in number theory. It's still open. Okay, so you see some applications of identity theorem that allows you to define something called zeta function. And then of course, this is a very important problem in number theory. Now, in the last few minutes, I still have 2 or 3 minutes. So here you see zeta function is it's a function defined everywhere except at 1 point, right? So such functions, such points are called known as singularities in complex analysis. So or isolated singularities. So what is isolated singularity? So well, these are points, So suppose I have a point P. I say that this is an isolated singularity. Of f, if you can find a disk around the point P, maybe very small, doesn't matter, such that F is, call it radius R, holomorphic on GPR. So there exists this disk, okay? So such that F is holomorphic on this punctured disk, but not on all of GPR. For example, if you look at the function fz equal to 1 by z, see this is holomorphic on all of c except at 0, right? So 0 is an isolated singularity. Now, in the real line, when you have a singularity, it completely disconnects the line, right? There are two parts now. But in the complex plane, when you have a singularity, it doesn't disconnect the plane. You can still go around the singularity. You can move around the singularity, and by doing so, you can capture a lot of information about the function. And in fact, there are certain integrals in the real line, which are virtually impossible to compute using real variable technique. But by moving to the complex plane and then moving around singularities that comes from the function, it turns out that you can compute the integral very fluently. Okay, this relies on, of course, some generalization of Cauchy's theorem. I don't want to talk about that. It's called residue theorem. But this gives you so this is called residue theorem. So this gives you very powerful and beautiful application of complex analysis. Powerful and beautiful application. These are usually by remaining in the domain R, this kind of integrals are almost impossible to compute. Okay, I'm almost done. But you see, I also need to talk about maybe 2 minutes I'll take and tell about I wanted to tell about what people are doing in complex analysis. Of course, I cannot talk different kind of problems, but I will address at least one kind of problem here to complete this talk at least. So one kind of problem that people study in complex analysis is they are basically complex dynamics. This is only one type of problem. There are various type of problems, but unfortunately, I won't have time to talk about this. Maybe in the future we can talk about this. So what does people do in complex dynamics? They study iterations of holomorphic functions. So that is more precisely, given a point z, you want to know the fate of the following sequence: z, fz, f square z, and so on. This is in dynamics people actually study iterations, right? So this sequence is called orbit of z. Okay. So basically there are two types of orbits. One which are kind of stable. Stable doesn't mean convergence. Okay, it's something more delicate notion. I'll give you an example to tell you what I mean by that. So stable means kind of so the following. So let's look at a simple example to understand this. So fz equal to z squared, and look at disk. Now suppose I take a point P inside the unit disk, and you look at the iterates, right? So that is P, P squared, P power 4, and so on. Because absolute value of P is strictly less than 1, this sequence will go to 0. Right? Not only that, you see, you take any tiny neighborhood of this point, because this is an open set, right? So I can draw a disk around this. And what happens is that you take no matter whatever point in this blue region, they will also, the iterates of them will also converge to 0. So this kind of points are called, orbits are called stable orbits. Okay. In fact, so I should also mention that stable doesn't mean only convergence. So if you take a point P outside the disk, then the corresponding iterates will diverge to infinity, right? And again, if you take a tiny disk around this, the same thing happens. You take any point from the disk, they will shoot to infinity. So for points inside the disk, for points outside the closed disk, the neighborhoods of this, there exist neighborhoods where iterates converges or diverges to infinity. Even these points we call stable because at least they always have some fate. Where they are converging, where they are going actually. They have some aim. So these kind of points are called stable. On the other hand, if you take a point on the circle and you look at the iterates, it will simply go around and around the circle. Nothing you can say more, right? So these points are called, in fact, something more actually. You take any neighborhood of this point, there are points which will go to infinity. There are points which will go to 0. So these points are called unstable because nearby them there are points where they show chaotic behavior. So there are two kinds of orbit. One is stable, one is unstable. The points for which the orbits are stable, they're called the set is called the Fato set. And the points where you have this, in this case this set is called Julia set, where you see basically chaotic behavior. So the central problem in dynamics is to understand these two sets given a function. Of course, we do not want to consider a very simple function like this. There are different kind of functions, and we want to know the Fato and Julia set. And problems related to sometimes you cannot basically completely determine the set, but you want to at least characterize this kind of set. This is one kind of problem that people studies in complex dynamics or more generally complex analysis. Okay, so I don't have time to talk about the several variable complex analysis, which is even more more interesting properties one is able to see here. But maybe we can talk about that in some future talk. So I think this is a good point to stop, and thanks for patience. I don't know how many of you already are still there, but thank you. I'll stop here.
Does anyone have any questions? Feel free to ask over the mic. Maybe there are some questions in the chat box.
Okay, let me see.
There is one question in the chat box.
So simply connected. So which theorem? Maybe the Cauchy theorem. Simply connected, as I said, is that allows you to shrink a loop. You can more generally there are general versions of Cauchy theorem also where but you need to use something called homology and all, chains and all. This is more complicated, but Cauchy theorem has more general versions. Okay, so but that requires more things to develop. So I basically wanted to talk about, because simply connected intuitively it is very easy to tell that you can shrink to a point. So that's the reason I mentioned simply connected. Even in multivariable calculus, there's a fundamental theorem of calculus. When you say that something is conservative, basically you work in a simply connected domain, then you have theorems for conservative vector fields and all. Okay, this is required so that the path integral is independent of basically path. To talk about indefinite integral. Anything else?
Okay, I guess not. So if there are no further questions, I think we can end it here. Thank you, sir, for a great talk. There aren't as many people who are here to begin with, but I'm pretty sure whoever stayed had a great time.
That's okay. Yeah, thank you. Okay.